Hello. In this video, I want to introduce to you the cyclohexane chair conformation. If you think about cyclohexane, which is a 6-carbon ring molecule, the most stable conformation is not having all of those 6 carbons in the same plane. If you take a look at this picture, you notice that the carbons are sort of have this zigzag pattern. Ultimately, when you look at it from the side view, it almost looks like a chair with the back, the butt, and the legs. So I'm going to show you how to draw cyclohexane chair conformations, but first I want to explain why cyclohexane does not exist as a flat molecule. So cyclohexane is a 6-carbon ring, and the easiest way to draw that on paper is a hexagon. Here's the line structure for cyclohexane. Now, I know I drew it flat on the paper, and if this molecule was made flat, like that, okay, I'm going to push this down so there are 6 hydrogens touching the paper, okay? And I can prove to you that this is flat. All the carbons are in the same plane. This is not like that picture at the beginning of the video, right? See, all carbons are in the same plane. So this is not actually a very stable conformation. You could actually see that these models have some strain. Look how that bond is bent inward. It's concave, okay? So that's one thing going against it. The other thing is that the internal angle when you have this flat molecule is actually 120 degrees. And so you know that a hexagon, when it's flat, okay, this angle is 120 degrees. That is far from ideal because this carbon right here is sp3, and the synonymous bond angle for sp3 carbons is 109.5 degrees. So when it is flat, this experiences pretty bad angle strain. 120 degrees is far enough from ideal, 109.5, and hence when the molecule is flat, there is pretty severe angle strain. And that strain is manifested by having these bonds kind of bend inward, okay? Because that angle really wants to be 109.5. The models are made to have that angle be 109.5, but in a regular hexagon, that angle is 120. There's another strain that maybe you caught when I held it sideways. Now, if I look down any carbon-carbon bond, you probably have studied Newman projections, where you look down a carbon-carbon bond and you have one or two conformations, either stagger or eclipse. Well, take a look at this carbon-carbon bond right there that I'm pointing at. When I look down the front carbon to the back carbon, what does that look like? Those carbon-hydrogen bonds are eclipsed, right? They're not staggered. So that's the second thing that's going against having the cyclohexane be flat. You have eclipsed bonds, also eclipsed bonds, and which bonds? CH bonds. So we're looking at it like a Newman projection. And what is the strain associated with eclipse bonds? It's torsional strain. There's angle strain, and now we've identified also torsional strain. The third strain that we know, steric, does not exist because everything's hydrogens. There are no big groups of atoms that are bumping into each other. Okay, so again, a couple things going against having cyclohexane be perfectly flat. So, how does cyclohexane actually exist in real life? How do six-membered rings exist in real life? Well, glucose is a six-membered ring, and glucose exists as a chair conformation. So I'm going to take this cyclohexane, and you'll practice when you have access to models. I'm going to push, let's try, let's push, give me 1 second. Let's push this carbon on the right up, and push this carbon on the left down. Do you see how the 6 carbons are not in the same plane now? And actually, if I lay it on the table, it's laying down on only 3 hydrogens. These 3 right here. 1, 2, 3. Going straight down. That's a chair conformation. By the way, look at your bonds here, the white ones. No strain, right? They're not bent inward. I should have wrote that down here. Because of the angle strain, the sigma bonds, do you remember? Let me show you again. They were bending outward or inward? See, they were bending inward. They're a little bit concave. Sigma bonds, concave. Okay. Okay, let's go back to what I call a chair conformation and look at it from a side view. You know, we're going to have to learn how to draw this. You're going to have to learn how to draw both chair conformations. That chair conformation and this one right there. You may not catch the difference. You will in just a bit. So let's go back to this chair conformation. Okay? By the way, when it's in a chair conformation, okay, here we have flat. What about what I call a chair? And you'll see also why I call this a chair. Look at the down the carbon-carbon bond, any carbon-carbon bond. Let's take a look at this front, this back. Ooh, ta-da! That's staggered. So we got rid of the torsional strain. In the chair conformation, there's no torsional. It's staggered. That's pretty surprising. If you first see it, it's staggered. What's staggered? Well, the conformation's staggered, right? Okay. I've delayed long enough. Let me show you some tricks how to draw what I'm holding right now, okay? You're going to start out with 2 parallel lines that are offset like that, kind of diagonal going downward. Okay, so I'm going to keep that there, and I'm going to start again. There. Next, we're going to draw the head or the back of the chair. What chair am I talking about? Let me use a different color. So here's the back. Okay, and then I'm going to draw I'll call it the feet of the chair, or the legs of the chair. Okay, that's a 6-membered ring, just like this, but now I'm drawing it as a chair conformation, right? 1, 2, 3, 4, 5, 6. Take a look, and you tell me if you believe that I drew exactly what I see the carbon skeleton shape there. Okay, I know it's kind of difficult, but you see what I'm pointing at now? I'm pointing at the back of the chair, and what I'm holding now, the carbon on the left, that's I like to call those the legs. Okay, if you could imagine a stick figure lounging, butt, legs. Okay. Right, hands behind the head, just relaxing on the chair. So this particular chair conformation, the person's facing the left. Okay. How do I make the chair face the other way? Well, I'm going to start out a template like this. Two parallel lines now sloping towards the southeast. Okay, let's see if this works. Oh, I hope it works. I'm not great at drawing the chair facing the other direction, so I'm a little bit nervous. I'm going to take this point and I'm going to push it down. Okay, make the head the feet. Make the head the feet. Yeah, I'm not that great in this direction. Make the feet the head. Okay. Alright, so now my person is, his back is here, his butt's here, and his feet is hanging off on the right hand side. Again, he's waving high, and he's just lounging. The fact of the matter is, every cyclohexane has two chair conformations. Always. So every cyclohexane has two chair conformations. And just like you're able to determine the stability of staggered versus eclipse, like the two conformations of a Newman projection, the two chairs may have different energies, and you'll have to figure out which one's the more stable. But we're not quite there yet. Okay? Now, if you followed what I was doing in my drawing, I drew this chair based on my model. Do you see how the back is on the right? I know it's, again, hard to see. It's the chair is like a lounge chair, and it's kind of tilted this way. Okay? And the back is here, right? And the feet are going to be here on the left. So how do I get this chair? It's facing the other way. You're going to take the head that I'm pointing at, and you're going to make it the feet. And you take the feet that I'm pointing at, you're going to make it the head. And you're going to kind of square it off, because you want the bottom to have these three hydrogens going straight down, the ones that I'm holding right now. See those three hydrogens going straight down? And then look at the chair. Do you see where the back is? The back is now here on the left. The butt will be here, and the legs will be hanging out here. Okay? Like that. Okay. One last thing. This is an introduction again. You need to be pretty good and comfortable drawing chairs before we talk about, in the next video or next class, stability. This is called chair flipping. It could go back and forth. And we're missing one important thing. The hydrogens. There are 12 of them. Oh my goodness. How are we going to draw all 12? Let's get back to this original chair. Okay? I'm going to do a chair flip. Boom. There we go. See, some are straight up. Some are straight down. Some are off to the side up. And some are off to the side down. Let me show you, and this will be the last thing for this video. Let me show you that. So let's draw practice. When I was a student, there was an exercise, draw that chair conformation 100 times. And then draw that chair conformation 100 times. Get it to where your muscle memory is trained. Okay? So again, I'm much better drawing the chair in this direction than in this direction, I think. Oh boy, still not my best work. Let's find the hydrogens. 12 of them. There is my chair. Let's start here, okay, at this corner. So, do you see it's tetrahedral? No angle strain. No angle strain. Unlike this, which was a 120. So let's add that here actually. No angle strain. Beautiful. We eliminated all the angle strain. We eliminated all the torsional strain. There's no angle strain because now every carbon has a bond angle of 109.5 degrees. Okay, enough chit-chat. The first hydrogen that I would draw on a cyclohexane will be this one going straight up on this far right carbon. Okay? Straight up. H. Now take a look at that carbon. Okay, hold the chair steady like that, so it looks like this. There's a hydrogen going off to the side, slightly down. Slightly down. There are two descriptors per hydrogen or group on a chair. The two descriptors are either up and down and equatorial axial. So I call this axial up. Axial means straight, up or down, okay? Going to the side, that's called equatorial. So this is equatorial, down. You got it? Now here's a trick. If you could get that corner right, the northeast, New Jersey, if you could get that corner right, and you can see it on your model, the rest of the hydrogens alternate. What do I mean by that? Axial up, next carbon, axial down. Next carbon, axial up. Next carbon, axial down. Next carbon, axial up. Last carbon, axial down. So when you're drawing your chair conformation, you do need to have those first two lines kind of offset, so this line that goes straight up doesn't hit this carbon. You kind of want it to go slanted a little bit. Okay, so make sure that this end of this line it's not directly underneath here, and that will give you free range or free space to put a bond straight up. Okay, just like that one right there. Okay, so let's label at least one of these. That one, axial down. Let's do the pink. Equatorial down. Equatorial up looks like this. Okay? What does equatorial down on this carbon look like? So, some students have trouble. Does it go to the left or does it go to the right? Take a look at your model. It's this carbon right there. It's the third carbon. 1, 2, 3. We should number this. I started up here. 1, 2. It's the third carbon. So let's take a look at what that hydrogen equatorial is doing. It's right there. It's equatorial down, but do you see how, from our point of view, it's slightly to the left? Slightly to the left. Okay? Aw, man. What color should that be? That should be pink. Equatorial down, but my model's also telling me a little bit to the left. Okay, equatorial down, equatorial up, equatorial down, equatorial up, equatorial down. Oh boy, carbon number 6. So in this case, it's the opposite of here. Equatorial up, slightly to the right. That's carbon 6, right? 4, 5, and 6. Do I have 12 hydrogens? I do. 6 axial, 6 equatorial, 6 up, 6 down. Okay? One more label, and then I'm good to go. This is equatorial. Color. Equatorial. Up. Okay, slightly up. Slightly up. Now the thing is, to draw, I'm not going to do this here, but to draw the other chair conformation, you want to keep track of carbon number 1. That head swings down to become the feet, and this feet carbon swings up. That's how you do a chair flip. So now carbon number 1 is now this one right here. Carbon number 2, carbon number 3. I will let you discover on your own. On this Florida, in the southeast, am I going to have axial down or am I going to have equatorial down? That is so essential, okay, that you are able to draw the hydrogen so it looks tetrahedral. What will look ridiculous, and I'm not going to even draw it, is if my green up bond was slanted. That's not tetrahedral. Look, that's tetrahedral. Right there. One up, and these three like a tripod. That's tetrahedral. That's what it should look like on paper.